So, let us start this lecture with a thought process. Belief of being a divine person is the ignition switch for realizing your potential lying dormant in your mind. So, coming back to that, like what I was telling, that in the last lecture we derived very simple way the root mean square velocity of the molecule, right, considering the kinetic theory of gases. And now in that case we did not really consider the how the distribution of particle we will be doing today. But before taking up that, I want to continue from the last, that we had derived a relationship between for the VRMS, right. If you recall that VRMS is equal to 3 RUT divided by molecular weight root over, right, yes or no, right. So, now if you look at, we will take an example just to have a feel what will be the velocity. I had asked this question in the last lecture, right, what will be the order of velocity. Let us consider a simple molecule, right, for nitrogen gas, right, and for that I need to find out, right. Let us consider the 300 Kelvin, like at 300 Kelvin what will be VRMS, right. This will be 3 into RU, RU is your universal gas constant. So, I can use 8134 into temperature 300 divided by molecular weight for the nitrogen is 28. Okay. So, if we use your calculator and find out, that values will be 511.32 meter per second. If you look at the molecule, nitrogen molecule is moving at a very high velocity, right, even higher than the speed of sound, isn't it? Such a high velocity it is moving. And of course, this is a very simplified theory. Of course, if you take consider little different, then it may be lower, but that will be that order. It will not change, order of magnitude will not change, okay. It will not be 50 meter per second. Now, if I increase this temperature to something, let us say 1200 Kelvin, what will be VRMS? What it will be? Just multiplied by 2, right, and that will come 1022.64 meter per second. Because everything is same, you are just increasing temperature by 4 times. So, square root of 4 is 2, therefore, it will be 2, that is all. Now, if you look at the temperature is higher, the velocity is becoming much higher. That is the reason why at high temperature some reactions may occur. At low temperature reaction will be very reaction will occur, but very minimal, because the collision will not be there, it will not be moving at a high velocity, right. So, now till now what we have done, we have to consider the particles, of course, number of particles per unit volume, like number densities and other things. But in this case, what we have assumed, the velocity will be isotropic, like kind of things we have assumed, right, and it will be that all particle will be moving with the same velocity, yes or no. But is it possible? It is not possible, right. So, why it is not possible? For example, let us say only nitrogen gas is there, container, but is it possible each particle will be moving with the same velocity? No, even in the same direction, no. Why? Because when there is a series of collision is taking place, right, even in proper orientation, that lead to a higher velocity. Let us say there is a head-on collision. What will happen? Head-on means two molecules are coming and colliding head to head, right. We do head-on collision in our interaction with the people, then there will be a quarrel, that might be some problem, like hata-hati ho jata hai, right. Exchange of word will get into the physical, right. So, head-on collision, Head on collision means both will be coming to the standstill. There might be a zero velocity, right, or maybe a small velocity. So therefore, there will be wide range of velocities each molecule will be having, even though it is at low temperature, it is at with the same molecule, let us say for nitrogen, right. That means molecular speed are not same, right, okay, or I can write down speeds of molecules, okay, speeds of molecules are not same even for same kind of species or molecules, right, let us say nitrogen, at same temperature, pressure and same volume, everything same. However, there will be a distribution, right. Hence, there will be distribution of velocity of molecules, right. And if you look at statistical way, right, one can see, keep in, but however, keep in that molecular speed at equilibrium is distribution is steady, right, distribution won't vary. If distribution will vary, then there will be problem, okay, isn't it? That means the molecular speed at equilibrium, right, distribution of molecular speed at equilibrium will be same. However, distribution of molecular speeds are same at equilibrium. Of course, we are considering equilibrium case and other things. So, and this distribution is basically given by the Maxwell, right, and that is known as I will be not getting into detail, but I will just mentioning that the Maxwell speed distribution, that will be, this is F, right, V is the velocity, 4 pi molecular weight, 2 pi RUT E molecular weight V square divided by 2 RUT is equal to V square. Keep in mind that this V is the molecular speed. Now, when you plot that thing, right, so that will be basically number density, right, that will be dN by N, this is change in the molecules, right, what you call number density by the number density, that means volume cancel it out, right, will be equal to what is that, F V into dV, and this is, what is this dN? dN is the number of molecules having velocity between V and V plus dV, with basically the dV in between, the what is that, like in between, right. So now if you plot this thing, will be number of molecules called vertical this thing, like, and molecular speed, this will be meter per second, right, you can say, and you will see that this is having Vp. What is this Vp? Vp is the most probable velocity. Vp is the most probable velocity, and from this you can really calculate Vp will be equal to 2 RUT by MW, and this is V is basically average velocity, right. V dash will be 8 RUT pi mw, and Vrms already we have derived, this root mean square velocity is equal to 3 RUT by mw. Keep in mind that Ru is your universal gas constant and T of course the temperature, and mw is the molecular weight, right. Let us say this thing, relative number of nitrogen molecules we are considering at 3 different temperatures. That means if I will consider that 300 Kelvin, right, of one temperature, you will find the velocity is here in this range. If you look at is something in this range, it will be something maybe 450 kind of temperature is coming at that, it is having higher what number density, right. But at the lower temperature it will be low, and then at the temperature the velocity of the molecules will be lower at the less number of molecules will be occurring in this lower temperature and also lower velocity range, right, lower velocity range. And if you go to a higher velocity range, the number of particles will be very low, right. You let us say this temperature, the number of particle will be very low, like, are you getting? But as it is temperature increases, if you look at the number density for a particular temperature, it became higher here, right. Again velocity will be higher, let us say something 600 meter per second. And as the temperature increases, right, what happened, the probable velocity is also increasing, right, peak velocity values. And this range, if you look at, it will be more number of particles are coming. And that is true also if you consider other way around, that we have seen that V is basically whether it is a average velocity or probable velocity or the RMS velocity is proportional to 1 over the molecular rate half. Now this corresponding what I was discussing earlier, it is T half power to the, right. The molecular weight means is basically mass. So oxygen, the molecular weight is what you call higher, right. So you will get the molecular speed is very low, and number density here it is higher, where number of particles, more number of particle will be having lower velocity. Of course there will be certain high range or the certain molecules will be having higher molecular speed, but those numbers are very less. Similarly nitrogen and then water and helium is a very lighter gas, therefore his particles probable or the more number of particle will be having higher velocity, right. Now let us look at what is happening in the collision theory, because this we have talked about kinetic theory of gases. Now if you recall what happens really during the chemical reactions, it is very simple, I have emphasized several times, that is there will be formation of new bonds and breaking of old bonds, right. Of course it does happen, right, in our interaction, isn't it? We may keep in memory, but something will be there. So and if it is happening, question is why does it happen? Because there will be collision, there will be interaction between the molecules, right. Molecules will be colliding with each other in a random motions, right. And even if they are colliding each other, like is it like there will be some reaction taking place? Will it be taking place? Need not to be. There is a the certain molecules will be have certain higher energy, right, such that it can lead to a breaking of bonds during collision, and it should be properly collided properly, orientation, at proper orientation it should be collided, right. So that means you will have to look at condition of the dissociation of bonds, that as I told, the colliding molecule must possess higher energy than the mean energy, right. For example, I am talking, it will be having some effect in your mind, right, provided a person is having little higher energy level. So, similar way, there will be not that all interaction will lead to the reaction or all collision need to be reaction, there will be depend on what is the energy level you are having, right. Leaders are those who are having higher energy level, higher better ideas and other things, right, similar manner. So, that is what you call, like if you look at reactants, it will be there, but here it need not to be, but there will be some higher what you call energy level, that we call it as a activation energy, right. And this is of course will be getting to a higher energy level, and then reaction will be occurring, then after that energy level will come back, so that getting to the product. And keep in mind that this is the activated complex. We will be discussing little bit about activated complex little later on. And whenever this collision is taking place, then we need to look at what is the probability of a molecule possessing certain amount of threshold of energy, that we call it basically activation energy, right. And this probability is proportional to exponential E RUT, and this E is your activation energy. If you look at this kind of term, we saw in the what you call speed distribution, Maxwell speed distribution, right. And also multiplied by the S. S is your steric factor, that will tell you whether it is proper oriented or it is collided at a proper orientation or not, with proper orientation or not, right. So, just to summarize, what are the condition of chemical reaction to occur? If you look at, the suitable molecule must collide with each other, right. Suitable molecule should collide each other, right, and molecules must collide with proper orientation, and that will be basically quantified by a steric factor. And colliding molecule must possess energy greater than the threshold energy, and E we call it as a activation energy. This E is basically known as, E is the activation energy. Of course, this is about what you call collision theory. What we are going to do is basically look at how we can relate this thing to the reaction rate, right. That is the basic idea. Okay. So, having said this thing, let us say there is a reaction, bimolecular reaction we are considering. Let us consider A is reacting with B going to C plus D. And if you look at, I want to find out basically what is that, dCA by dt, right. So, if you look at from the collision point of view, what I will have to look at, I will have to find out is equal to, right, of course this will be minus because it is destroyed, right, is consumed. So, therefore, it will be minus, I can say. This is number of collisions taking place, right, per unit volume per unit time. That means, okay, and then I will have to say that then what is the probability of successful collision during reaction or for a reaction to take place. That is probability of successful collisions for a reaction to happen, right, into the what you call number of moles of a species, right, A, you can say kilomole of species A, right, by the number of molecules, number of A molecules. Make sense, right? But if you look at this first term, what is that? This is basically collision frequency per what? Per volume. See, if I say this is Z, let us say A, right, or A by this will be volume. If I say all the A molecules are taking place, of course it won't occur, right, but let us consider that, or I can consider B, right, A between B colliding, right, per, this is basically collision frequency. Frequency means number of collision per unit time, right, into V is the volume, into probability, what is that? We have already seen, that is E by RUT, into steric factor, S is the steric factor, into what is this term? This is nothing but your AN. AN is your Avogadro's number. Make sense? Now I will have to find out this collision frequency, because this I can take from the what you call Maxwell distribution, right, and this I can take. Now we will have to determine the collision frequency, right. I think we will stop over here, right. We will be discussing about the collision frequency by considering in a simple collision event, right, and later on we will look at basically how we will relate to this and the reaction. Thank you very much.